you for kind introductions. So I'm Tetsuya Ogata from Waseda University. Actually, I'm come from the field of the robotics. Usually the topics and different from your interest. But I believe that we robotic research are really influenced and impressed by the findings from the neuroscience and robotics. I would like to show some example on the concrete examples in robotics. How to apply such kind of idea, and I hope you enjoy the movie. and so actually, AI now is almost in the deep learning, and it shows quite great performance, especially handling and image and text and voice and so on. Once it's digitalized in the cloud, it's obtained a huge large data, and it's not easy, but could be obtains very good performance, good models show the performances. But actually, from the viewpoint of robotics research, it still remains a very difficulty to apply the deep learning models in a real robot. Actually, what's happened? What's the reason? I believe that we could think about the next generation AI by thinking of this kind of questions. So this slide, I roughly try to summarize an approach. It's how to use the deep learning in robot applications. The first one is recognition. Because as you know, deep learning shows very good performance, image recognition, and speech recognition. In the input part in the robot, deep learning it could be applied and easily to improve the performances. And the second one is reinforcement learning. It's also a very, very promising, strong approaches, especially showing the good result in the virtual spaces like the game. Keeping the trial and errors and maximizing obtained reward. But I think both approaches are very, very common in the machine learning. They try to obtain the optimal and the best model as much as possible. That means requires huge data. And once it's established, the model could apply to many different types of situations. But if we consider the real environment, we always have such inevitable prediction error, error between the real world and models because world is open. So very hard to obtain. What is optimal? It's very hard to estimate it. Of course, once the task is given, it could be. But I believe that the model should handle such kinds of the error, inevitable error. Before the hypothesis, based on the hypothesis, learning is always incomplete, complete models. Sorry, actually, I don't explain the details here, but some parts of this principle predictive processing is very, very impressive for the robotics researchers. Because actually here, then it could be explained that by the modeling training, it's always try to predict it, but not just on these learning. It's including the parts of the how to decrease the learning, how to decrease the prediction error. By changing QZ, and it could be say the kind of the perception and also the action. So this part is very, very attractive for the robotics researcher. In the control systems, feedback control or something like this. Usually robots always use this kind of manner, how to change the motion to keep the keep the trajectories. But this model seems to be not to keep the trajectory, but to how to decrease, how to minimize prediction error. That kind of sense might be a very impressive and might be a very important idea to the next robot controls. And here is actually my third example to try to replicate very small parts of such as the predictive processing in the robot systems. You see now the robot can hold the tout. Actually, maybe some of them are not thinking about this is a difficult task. But for the robotics researchers, I believe that many knows it's kind of very difficult. Because now the conversation already explained. Usually the robotics researcher needs to some kind of a calculation of the safe steps cognition and planning generation. And especially the cognition parts, usually so that they prepare some 3D model, CAD model for the target object and the robot system or something like this. And after the recognition of the vision, so then it can estimate how much distance from the camera and the direction and the posture of the object, and which part is all graspable. The parts, this is usually given by the human designer. And then the calculate is inverse kinematics and also sometimes needs to optimize and generating the trajectory. Very many processes. And and this case towels, so it changes shape. Of course, there are some studies to try to modeling these towels and clothes, so it could be changeable. But it's very hard and usually takes a long time to start the motion. But now you can see this robot generate the motion very smoothly and repeatedly, keeping very stable conditions. What happened in this robot? So actually, this one is unknown towels. So that is was not trained. So for the networks. And next is you can see the book. Book is of course an untrained object, but it works very well. And this is one scheme proposed in 2012 in the first. So it's combined to the autoencoder and the recurrent neural network. Now there are many studies who have a similar architecture on the combination of the recurrent neural networks and autoencoder. But actually, I said we used it 10 years ago anyway. So and this one is in the training phases. So now he becomes this robot and operates and gathering some success experience. So for the following towels, we prepared 3 different types of towels and placed in different positions. But an all training data, the training trial is 50, just 50. And after that, this is so input, so actual camera images, and this is a predicted image. And this one is so used to refine the input to the image. So what happens here? So actually the motion and vision, so sensory motor is sequence driven. And the recurrent neural networks and autoencoder stores the past experiences. Then so by repeating such motions, so there could happen some entrainment, the coupling between the environment and the neural dynamics. Actually, for the robotics research, it might be easier to think about passive walking or such kind of model or non-linear oscillator with something like this. So a body and oscillator and environment is coupling, so walking then automatically generated. And thanks to the deep learning, we could be enhanced this concept to the very huge size of the input, like the image and tactile and any type of sensor. Then, so it's, we show the demonstration in 2016, the multiple exhibitions. And then now we collaborate with multiple companies like this. So the first of them is just a demonstration, but so powder weighing or liquid weighing or something like this. This one is actually now applied to the real industrial robot systems. Actually, AI 模倣学習、そうですね、written in 漢字。but this release in the last year. But very preliminary model is currently used, and I hope that it improves in the future. So that by adding especially focus on the attention. So here is an example and modeling the attention with collaborated Hitachi. And so target is an opening back, opening zipper. So now you can see the robot started picking the zipper. So that means so grasping conditions always changes. But this robot is training with torque and tactile sensing in the fingertips. So it tries to predict to the image and so also tactile information and try to reduce the prediction error. So that means automatically generated trajectory. And so this is a scenery to how we apply to attention to one of the examples. So here, red point means the attention point. That means so actually prediction error of this part is becomes large, and other is equal. So then so robot can adapt to the change of the environment, for example, background color, or and also if human wants move to the object, so it can adapt it. And this scenery is a very symbolic scenery, I think. So here, this is a real scenery. And this is so imagine, so try to decrease after the couplings, so environment and neural networks, then you can see the, so attention path, this object is only replicated. And this one, other object is now disappears. So that is so very kind of making a fake image, kind of so uh, like a virtual image to complete the task. Such kind of sense is, can be explained as a result of the coupling. So this one is how to implement. So I can actually, so I don't have enough time in detail here. But so here's attention. Currently, so visual attention is often talked about just to focus on the so image saliency, the important complex pattern or something like this. But here we focus on the attention should be generated as a result of the prediction. The total loss is in how to generate predict future images. But so it's impossible to predict the image completely. Okay? That is very important. So the target is not to obtain the perfect model. It should be to accept the kind of the error by ignoring the not important things. So here's the target here, and so try to predict the which part and which kind of the feature is important. And this here is a recurrent neural network. Neural network also accept to the joint angle, so that is so connected to the have the tendency to the point. It could be handled by their own hand or something. So actually, the scenery is in the back. So you can see the hand is reproduced because hand is self-voice. This is very interesting. And next topic is so handling the tools. So which get awarded in ICRA. ICRA is in top conference in robotics field. And this one where try to handling different types of objects and gradient. So final goal is develop the cooking robot. And the important things here that is not recognize objects by only using visual information. So you can see the phases and also interacting phases. So by gathering the data during the interacting such target object, so it measures the tactile sensor and torque sensor information. So it stores to the latent space, and after the result, it could generate to the selected tool and forwarding it. So here is a training object, and here is an untrained object. So actually, so in this research is so interacting manner, interacting motion is fixed. But once it can keep in the fixed motion, so latent space is in the recurrent neural networks in that encode used for the encoding to the how to the torque sensor and image change it. And so after the latent space value is obtained, it's used to decoding to the selecting both tool and generating motions. And we could analyze what types of information stored at the latent spaces. So you can see, actually, this is very hard to find which part is important or not. But so you can see, this one is separated which tool should be used. And this one is in a category to the each target object. And this one is so representation untrained target. So, and actually by including a tactile sensing and so torque sensor, so the performance, so success rate drastically increase. The vision, using only the vision is very hard. So not before the handling, but after the handling or interacting, that is very important. And the next topic is so whole body learning. So it's recently accepted in science robotics. Science robotics, one of the top journal in the robotics area. Actually, we robotics field don't have so such many journals with high impact. Many reasons before the science robotics, highest is 5 or 7 or something like this. But now, then, thanks to the many professors, so we developed we have science robotics, and so now this paper is selected for the cover of these issues. And so you can see now robot can move reaching the target, opening the door and passing, and very stable. So now you can see during the motion, the human can interrupt it, sometimes supported it. And bottom two cases, untrained doors. So it could be adapted to some kind of change of the lighting conditions, the color change of the doors. And the important things, so same as in towel folding, it could be repeatable. So that means very important tools and safe as in so controls and real robot systems. What happened here? Actually, this is come from inspired from the neuroscience, so mixture of experts mechanisms. So structure prediction model. Now, the towel folding cases, we just only one predictors. But here we prepare totally six predictors for approaching, opening, and passing. And so based on comparison of the prediction error, the selector is selected some module to control the whole body control. So it's quite efficient and very easy to the modeling. So not required to the robot model, not required the door models, not required the control systems. So just trained, actually in this case, is so each motion approaching and opening and passing, so it usually takes 20 or 30 times. So in total times actually, but actually it could be acceptable. And once so actually in the back, so opening doors and pulling it, so Hitachi staff and some complaint you shoot to the back. so then my colleagues try to implement such kind of motion in one day. That is very easy to apply. So now we try to use these new features. And so maybe I need to summarize, so I cannot explain the detail here. But so actually, before this morning, I received a mail from the computer. So I added some topics on how the goal is handled in the recurrent neural networks, our models. So now, actually, very old studies 3 years ago, but here we think about very preliminary study to the collaboration with robots and humans. And so now trained with block couplings, and so human could interrupt. Actually, so robots bring the object, and the human combines each part. So if prediction error happens, its error is backpropagated, so the backpropagation through times. So the goal image in the robot goal could be directly adapted. So this is a real scenario to the Excel synergy. So first reason robot expected this one, but so by replying to the humans on how to combine it, they could change the goals. For example, maybe I can skip. I should skip this one. And yes, first, so it expected the final goal here, but now he put in the red one first, so the goal is now changed like this. And another motion is given, then the robot can be adapted. So goal-directed behavior is kind of adaptable, be developed in models. And now I think so in deep learning people, especially game, there are some studies related to this one. And maybe, sorry, to the one minute. So I need to like to explain the Moonshot project. So supported Japan's cabinet offices, the quite large project aims to develop a robot which can be supported in human daily life. It's set in goal 3. Actually, there are main goals, and we included in goal 3. And then now we developed this type of human robot, because Waseda is the first university developed the first human robot. So the human-like shape is the optimal solution or not, I don't know, but as a first step. So this robot, this motion is generated without any learning. So just using impedance control in each joint. But it's easy to generate such kind of motion. So thanks to its softness with the body. So, but at the same time, it can generate quite big power. So using just only one arms, it could be moving at 20 kilograms, maybe more. By using both hands, so I saw some demonstrations, the student completely bring those like this. So then, actually, believe that so the robot hardware itself is so very good hardware now. So motors and tactile sensing and vision, and could be implement many degree of freedom. But actually, very hard to how to control it. So over 10 years, we could develop such kind of humanoid robots, but it's very hard to know how to use it. But so I believe that our approach could be help to such kind of control the robot systems. So we call it here as so co-evolution between robot and AI. And now, so now we started in a Moonshot project. We started to collaborate with the Alan Turing Institute with Vijay Kumar, who is a program director related to robotics. So now, in March, we had a webinar, so on the science webinar supported by science, and like this. So actually, it is still open, so you can see it. Sorry for this. That's all. Thank you.
Thank you very much, Ogata Sensei. We can accept several questions from floor and online. Is there any? Okay, I will put some question first. Thank you very much for great videos using the learning as mechanisms. So could you tell me what is the most difficult part in using the deep learning or neural network learning scheme in robotics?
So actually, so in the past, so in general, it's very hard to guarantee the stability. So actually, then I show the demonstration leaping, the tau holding, the opening, but it's a kind of result, so good result. So actually, so now it cannot analyze based on such kind of conventional control theory. So we cannot say estimate how to stabilize it. So actually, the all motion is encoded as attractor of the recurrent neural network, but we cannot see the complete analysis of the bias around the attractor. So maybe that is one of the difficulties.
Thank you very much. Any other question? Yes, please.
Thank you very much. So I think one of the important components is the kind of attention mechanism.
Yes.
So for avoiding the learning a perfect world model.
Exactly.
So how does the system find such kind of attention mechanisms? Is it due to the bias of the data or other mechanisms?
In this case, we just firstly follows so conventional attention system to so maximize the obtained reward or some such kind of systems. And I believe that the attention so should be generated not just from the input value to the other result to the prediction. So that is this is one architecture to the here we select generate we prepared some point as attention point and how to arranges the point in the view to the decrease all image the error and prediction errors. But one of the difficulties in how to determine how many points is required. And so now my students use another attention systems not requires such a settings, but so maybe near future I will explain that.
Is there any other question? Okay.
Hi, it was quite a talk and got me thinking about human movement and basically a couple things that we've done. One is in the human system, you can't generate torques in real time. And so, but what you can do is if you have the kinematics, you can, because the spinal cord could integrate for it. So I just was wondering Have you thought about that? Because in vision we use basis functions. So when you go with kinematics, you could use basis functions for that. And I was curious if you've been thinking about these along these lines, or where just robotics has to be different.
Thank you very much. So actually, so now I think this is the preliminary stages. So just by imposing the joint angle directly, the network robot seems to be a success to the complete tasks. But so now recently, the student reported by using kinematics, so I think in university kinematics, some of the task is easily generalized. So I'm not sure which kind of the task is using kinematics importance or not. But so now is so just easiness. So we use such kind of ways directly end-to-end learning manner. Yes, but next target could be include such a kinematics analysis.
Thank you.
It's almost time. So thank you very much, Ogata Sensei.
Thank you. Thank you very much.
Now we can accept further question in the discussion. We would like to go to the next topic.